good name, Professor Barry Barish, Nobel Prize for the discovery of gravitational waves in 1930. So it's an honor for us. Barry Barish will be in our department in this month for up to almost the end of March or something like that. And he will have also the opportunity to interact with researchers and students of our department. So, thanks for coming here. I am sure that this will be a great opportunity even for the larger public, students from the school, teachers and so on. So I would like to first, before the lesson, to introduce Professor Gaudio, the rector of our university, for the institutional greetings.
Thank you very much. Dear colleagues, dear students, it's a great pleasure and I'm very glad to bring the institutional greetings of Sapienza University to Professor Nobel Barish, who will give today the first lecture of the Eugenio Gaudio Chair for the academic year 2019-2020. The Enrico Fermi Chair has been established in 2011 by the Italian Ministry of University to promote knowledge of modern physics beyond university courses and to celebrate the scientific tradition of Italy and of this department. The universal genius of Enrico Fermi, has indeed provided long-lasting contribution in almost all fields of modern physics, from atomic, nuclear, and particle physics, to solid-state physics, cosmic rays, general relativity, and high-dimensional calculus. On each year, within an academic semester, the holder of the chair provides a series of lectures on Enrico Fermi. Lectures are open to a non-specialistic public and concern the research field where the chair holder has provided a significant contribution. This year, the Fermi Chair is to Professor Barry Barish, Nobel Prize 2017 in physics for his decisive contribution to the middle detector and the observation of gravitational waves. The scientific contribution to fundamental physics cover different domains, from the neutrino physics with the Fermi Lab experiments to observe the weak neutral current, to the search of magnetic monopoles with a macro detector, the first large volume experimental study in the INFN laboratory in the cavern of the Gran Sasso Mountain. He directed the macro experiment, providing important results on penetrating cosmic rays, including neutrino measurements and confirming the evidence of neutrino oscillation. A large fraction of this scientific activity deals with the direct detection of gravitational waves, that certainly represent one of the most important consequences of the general theory of relativity. Gravitational waves, are space-time vibration caused by the most violent phenomena in the universe, such as, for example, black hole collisions, supernova explosions, and so on. The effects are extremely big. They require the use of high sensitivity detectors. Since the 1970s, the two leading interferometers were devoted to measure gravitational waves. And from 1994, Barry Barish had a leading role in the LIGO project that in 2015 detected gravitational waves for the first time. Together with LIGO, the European Interferometer Virgo, that has seen the fundamental participation of Sapienza researchers and colleagues in both data collection and analysis, has allowed during the last years the observation of several gravitational gravitational wave signals, and among them the famous GW170917, noted as the birth of the multi-messenger astronomy. The 15 lectures given by Professor Barish represent a great opportunity for Sapienza community and for the public, who will have the possibility to learn or deepen some of the most intriguing mysteries of physics, from dark matter to gravitational waves, from the primordial universe to the new frontiers of this field of investigation. The physics department of Sapienza University was among the winners of a national competition for excellence departments, with a project focusing on gravitational wave research and the related scientific activities with the institution of the so-called Amaldi Research Center. So, we are very proud and very honored to have Professor Barish in our university, in this department that is dedicated to Enrico Fermi, and this room is dedicated to Edoardo Amaldi. I can say the right man at the right place. Thank you very much.
Okay, so let's start with the lecture. Thank you, Professor Fermi.
Thank you for the kind introduction. I'm very happy to be in Rome, very happy to be here, and to have the challenge of trying to give these Enrico Fermi lectures. I'm going to be very ambitious in this set of lectures. Gravitational wave, which you're talking about, I'll get to in January, so if you came only for one lecture to hear that, you have to wait. I decided, when asked whether I would give these lectures, to try to give a set of lectures that was accessible to a broad range of interested public that maybe don't know a lot of the technical details, but perhaps read the newspapers, see about discoveries in physics, and to also have something of interest maybe for some of the more senior people who understand more. So whether I can achieve all that, we'll see. But I've taken a particular approach, as you'll see, to try to do that. I'm picking topics that you tend to see or should see if you are interested and read the newspaper, maybe the science part of the newspaper. Or if you hear about a subject and read maybe Wikipedia, I want to give it at a level that can educate those of you who don't know a tremendous amount of physics, and while at the same time showing us some of the subtleties. So what I ask from you is to realize that parts of what I'll do you cannot understand if you're more general. But that shouldn't bother you, because I'm going to try to make enough of it accessible so that everyone that's sitting here can appreciate it, even if there are pieces that maybe are a little more sophisticated or require more background. So we're going to begin a journey through what I call the frontiers of physics and astrophysics. And I'm going to give it from an experimental point of view, which means the point of view of someone who actually makes measurements. And therefore, I'm going to spend a considerable amount of time showing you the kind of instruments that we use to make the discoveries that I'll talk about. It's often thought that physics is a field that moves forward with two kinds of populations, theoretical physicists and experimental physicists. And that is, some ideas come from theorists, they've been checked by experimentalists, or the reverse, that experimentalists see something in nature and then theorists have to explain that. And then there are some people that are somewhat in between. In fact, Enrico Fermi was one that was in both areas. There's a third area, though, that's as important, and I'm going to try to emphasize that, and that's basically technology. Technology is crucial to doing physics frontiers of physics. So as I present any one of these frontiers in physics, I'll present three sides of it. That is the theory that we understand, the experiment that has to be done, and the kind of technology that was used to do that. In order to do that, I'm going to spend some time teaching you at least the kinds of technologies that have been responsible in the past for the advances in physics in the last, say, 100 years. To set the stage, when we talk about the kinds of projects that people are working on now to explore physics in the future. I'll pick a selective set of frontiers in physics. LIGO, or gravitational physics, will be one of them. I'll also talk about other subjects that you've heard about, whether it's dark matter or the early universe that we all wonder how it all began, and so forth and so on. I have an outline. I won't follow it strictly, but I'll keep you up to date on what I'll be doing at different times. This cover slide, for me, illustrates aspects of physics because it shows the most elementary concepts. For example, a mass rolling down an inclined plane, something we learned in very elementary physics, magnets and magnetisms, to the atom, and then beyond. So we'll cover many topics in this course. I'll leave out many others. But we'll especially work our way toward you having some sense and understanding of the physics that's being done today, the modern instruments, the questions that they're trying to answer, and maybe some that are in progress already, the results that they're obtaining. So first, about these lectures. As the rector said, these lectures were made for a particular reason, but I'll pick from my findings that Fermi himself and these lectures were made to promote a knowledge of modern physics and beyond, which I'll try to do. And as I've said, this is the way I'll approach, as I just said, the way I'll approach it this year. So the first is a picture of Fermi. And let me just give you my understanding in a few words of Fermi himself, since we named the lectures after Fermi. He was born in 1901. He went to the Scuola Normale Superiori in Pisa and graduated in 1918. In 1918, he got his degree in 1922. He was a professor of physics then at the University of Rome in 1927 to 1938. And at that time, because of what was happening in Europe, he immigrated to the U.S. And certainly because of the Mussolini fascist regime here. Upon the discovery of fission, which was discovered in 1939 by Hahn and Strassmann, he immediately saw the possibility of the emission of secondary neutrons, and therefore what became known as the chain reaction. He proceeded to work with tremendous enthusiasm, this is in the U.S., and direct a classical set of experiments which ultimately led to the atomic pile and the first controlled computer chain reaction. This took place in Chicago in December of 1942. Actually, experiments that were done in a tunnel underneath the football field on a squash court that was buried in. This was a crucial step for the atomic bomb. Fermi accepted a professorship at the Institute of Nuclear Studies at the University of Chicago right after the war. So after World War II, he went to the University of Chicago, and he stayed there until his death in 1954. Chicago turned his attention to what we now call high-energy physics, or particle physics. That is, since he had studied and done nuclear physics as a student and as a researcher, and then worked on the atomic bomb, then he moved on to what many other researchers did, and that's to understand the physics behind the particles that were involved in the nuclear bomb and beyond. led to investigations into what he studied first, which is the reactions of what I'll teach you, pi mesons scattering of nucleons, and he developed the theories and did experiments on them. He was awarded the Nobel Prize, as you heard, and that was for his work on artificial radioactivity that produced the neutrons, and for nuclear reactions that brought about what we call slow neutrons. So that was Fermi. He's a person that, for me, played a pivotal role when I was very young. As a student in Berkeley, where I went to school, as an undergraduate, I studied the academic text like most students here would. And the first physics book that I ventured to read that was outside the coursework was this little book shown here called Nuclear Physics. It's a manuscript that's about 50 pages long. He had written it, and I read it as an undergraduate and appreciated first Fermi, who both explained it experimentally, approached it theoretically, and wrote it so concisely it was only 40 or 50 pages long. I don't know if it's available easily now, but it was had a big impact on me as an undergraduate who wasn't sure what I wanted to study. That nuclear physics or particle physics was a very exciting area to pursue, and in Berkeley they had all the large particle accelerators that had been built at that time. A more recent book, the one if you want to read a pretty good book, is written on Fermi, about Fermi, is Europa Physics, which came out about 2 years ago, and is a very readable book about his life as a scientist and about his accomplishments. So anyone wants to read about Fermi, I read this. This is the schedule for the year. The course will have, as I said before, 15 two-hour lectures. We'll have a break in the middle. I don't know how large the class will stay as we proceed. At anything like this size, I can't really entertain questions as we go along. So hopefully you won't be shy to come up with a 15-minute break and chat about whatever I'm talking about. So take advantage of that. We'll take a break at the mid-time of these lectures. The lectures will be given on the calendar shown here, but it's each Thursday of the formal academic year that the students have here at the university, except for one, when I have to be in China, so I moved it by 1 week, and that's November 7th instead of October 30th. Okay. Let me introduce myself so you know a little bit about who I am, other than having been awarded the Nobel Prize. I was born in the Midwest of the U.S., in Omaha, Nebraska. I moved to Los Angeles when I was about 10 years old. I went to public schools. In the U.S., that means we have private schools that parents pay a lot of money for. In public schools, I actually thought, by the time I was in high school, that I was going to write the great novel. A high school literature teacher gave me a novel to read, which maybe some people here read, that convinced me I should do something other than try to write a novel. And I've read it since, but a terrible novel for me as a 15-year-old to read. It was Moby Dick. I don't know who here has read Moby Dick. Moby Dick, which is a great novel, is one big metaphor. And a metaphor is something that me, as a 15-year-old, didn't understand at all. So the book is incredibly boring, especially those who have read it. It's a long, 100-page long chapter describing the great white whale, which if you understood the metaphor was okay, otherwise I think it was boring. So I decided I had to do something else with my life. My other occupation was that from a very young age I was a serious tennis player, a tournament tennis player. And but by the time I got to college, I minutes your time outside of class practicing tennis or in physics labs or chemistry labs or whatever. And I made the choice to go to labs and drop tennis after my freshman year in college. I went to the University of California in Berkeley, both as an undergraduate, and I got my PhD there. And it was transformative in my life. Really, I didn't know what I wanted to do. When I went to college, I thought I might play tennis or write books. And it was being in Berkeley, and it was actually the aura of discovery in physics in Berkeley at that time. For example, my undergraduate advisor was not Emilio Segre, who was the Italian judge's partner in getting the Nobel Prize for discovering the antiproton, which was exactly the time when I was an undergraduate. I came to Caltech straight from getting my degree, and that's my only job ever in my life, except for ones like this, or temporarily, but I'm still at Caltech. So I've had one job my whole life. That's not a very good story. I began my career then in experimental particle physics, but you might note that I've done many different things. I've basically done what the title of this lecture series is, that at every point in my life I've picked what I think is the frontier of physics where we can make progress by doing something. So I've moved around to different subjects my whole career, and somehow my bosses let me do that, so I was okay. Okay. And I got the Nobel Prize 2 years ago. You heard about that. So this is the series of lectures. Today's an introduction to what I call physics of the universe, which is just a general statement. And the general approach that I'll take is to go through more or less areas of particle physics very selectively through the fall, through the next 4 or 5 weeks. And then a particular area which I think is both very intriguing historically and in what we do, and will be in the future. And so I pick it, and that's neutrino physics. So I'm going to talk about neutrino physics. Neutrino is one of our most exotic particles for several weeks before Christmas vacation. And then after Christmas vacation, I'll spend several weeks on gravitational waves. And then I saved it for the last, what I call more astrophysics and cosmology, because it combines our knowledge of particle physics, gravitational waves, and so forth with what's observed in astronomical instruments. And so I'll try to pull them together as we reach more the end of the course. So, okay. So let's move on. I've decided to start by introducing you to the past. Not the distant past, but a book here which you can reach on the internet if you want to, or just listen to me or look at the slides. But if you want it more, you can find it at that website. I'm going to use it as a model because it's a model of, like, if we take a snapshot today, I can tell you all the great things that we'll do in the future and what we accomplished the last few years. But if I go step back a little bit in time, I can put this book in the same position we're in today and evaluate what they say, which was in 2002. So in 2002, the National Academy of Sciences in the US put together a panel of distinguished physicists and astronomers to do a study. And they did a study for about 6 months or a year, stimulated by the fact that it was becoming apparent that the distance between physics and astronomy was getting to be less. That there are areas that physics and astronomy were overlapping, and since we teach them and do them as 2 separate subjects, maybe it would be better if we learn how to work together more. And so we call that particle astrophysics or experimental cosmology or whatever the words are, it doesn't matter, but it was approached in order to basically do this. The book, the result of this study is very interesting in the way it's done. They spend part of the time looking at what we know, they call it. I'll show you some of that selectively. And that is mostly what knowledge we're building on.
And some of the recent discoveries at that time, like I could show you the recent discoveries now, are things like gravitational waves and the Higgs boson. We'll cover that later. But at that time, there was, for example, what's called the top quark had just been discovered. So they look at what was known at that time, and then they set 11 questions, and I'm going to go through most of those right now. They go through 11 questions saying that these are questions to focus on what we should do in the future. And we here, 18 years later, can ask which ones of these have been answered and why not if the ones haven't been answered. So we can look back and see how this looked like. And I'll try to take you through this a little bit. So the subject otherwise that I'm going to be doing, I'm going to wind my way into it, and by next time we'll be deeply into it, is understanding the elementary particles themselves, maybe later today if I get far enough, and where that's going as a subject, what its relevance is. You can summarize what we know about elementary particles amazingly in almost, I'll show you a different picture in a little while, but almost in this simple picture here. And this picture here gives us the description of our best understanding of particle physics. And people probably either know or have read, we call it the Standard Model. Standard because it's basically describes most things and we just use it to describe everything. But interestingly, using the word model. So the word model and not the word theory is because even though it describes almost everything, like I'll show here, in particle physics, there are great puzzles in particle physics that it does not describe, and therefore we cannot call it a theory. So as good as it is, it's a model, and it's up to the next generation to somehow evolve this model into a theory. We're looking for clues, how to do that. That's what is being done in laboratories like the CERN laboratory, is to try to find the clues to the future. The big discovery so far at the CERN laboratory is on the I'm not showing what I thought I was. So upper right-hand corner, this is the picture that I was just describing. And that is that nature, as far as elementary particles, is made out of these sets of elementary constituents. The ones in the upper left, the 6 in the upper left, make up all the particles that we see that interact strongly. That is, protons and more exotic particles. The ones in the lower left are the ones that describe what we call the weak interaction, radioactive decay. The red ones, the list of red ones, are the forces. We know that there's different forces in nature: gravity, the electromagnetic force, the strong force that holds us together, radioactivity, or the weak force. There's 4 forces. Those are the carriers of the 4 forces. And then there has been a puzzle for a long time that the model that we had for elementary particles was perfectly happy if the masses of all the particles was 0. But we know we live in a world where all the particles, including ourselves, made out of particles, have mass. And so the one in the upper right hand here is what's called the Higgs particle, which we now know is responsible for mass. So this simple picture tells you a lot about particle physics. I'll go beyond that some, but I'll describe first how we got to this when I move on to particle physics and then after I introduce these questions. So the first thing that they concluded in this report is what we know. So first was the most recent discovery as of 2002. And it was in that chart that I showed you. It was the heaviest of all the quarks. We never understand why it's so heavy, and so it evaded detection for a long, long time. And it took a very sophisticated experiment using technologies that were only developed as the discovery was being made. This is what I'll show you later is called silicon detectors, which gave fine enough resolution in space that you could separate these particles or reconstruct them. And that was done in a big detector in the laboratory called Fermi Lab in near Chicago. And that was done by colliding high energy particles, protons, at 1 TeV. That's 1,000 times the mass of the proton. And later I'll show you this experiment somewhat. But just like today, we could look back and say we discovered the Higgs boson or gravitational waves in the last few years. When this report was written, they had just discovered the top quark, and this describes how they made the discovery in a particular detector. So, turns out if we start looking at the particles that are made of these elementary constituents, the particles themselves, most of them have some lifetime, but they vary from particles that have a very long lifetime, like the neutron, lives some number of seconds, 140 seconds, to particles that decay incredibly rapidly, 10 to the minus 23 seconds. I'll show you how we learned about the ones that are very short-lived and the ones that are long-lived, because it illustrates some of the techniques that have been developed. We also learned quite a while ago that the particles that were in the lower left-hand part of that diagram, which I called leptons into the weak interaction, as far as we can tell, have no finite size. They're infinitesimal or less than we can measure in size. We always keep wondering whether they might be larger. While the particles that make up us, like the proton, which is in our bodies, has a finite size. And how big that is and what it's made of is one of the big puzzles that particle physics has grappled with for years. So we have we're used to having atoms which have electrons going around, but the nucleus itself is what I'm trying to emphasize, or they said that what we know is that it has finite size. The electrons are point-like, the hadrons, the neutron and the proton is made up of something that gives them finite size. This is the size. For some reason, it comes out backwards and upside down after I put it into PowerPoint. But that's the size that it shows. So that's one thing we know. And that was learned, that it has finite size and that you have the last particle, the top quark, just a few years before 2002. The other big discovery, or another big discovery that was just before 2002, so it's, again, what we know, is called, given a fancy name, it's called quantum chromodynamics. But what it is basically a description for the first time of what holds the proton together. What is the force that holds us together? What's the strong interaction that makes it work? This has been a puzzle with wrong theories for tens of years before that. Then a theory came out which was controversial at the beginning because the mathematics is divergent, has a lot of things that people don't like, but it turned out to be the key to describing not only the fact that life is standard, the finite size of the constituents which it has, but if you have subconstituents, which I'll talk about, which we call quarks, that they would be confined. This was a big, big puzzle for tens of years before that. That we have a theory, which I'm going to show you, that these particles are neatly made out of something we call quarks, but they can't get out. That always was unsatisfying. It was like you have a mathematical description, they can't get out. This, as I'll tell you later, gives a physical reason why they can't get out, a mathematical reason. This is called quantum chromodynamics. And what to notice is that on the left-hand side, there's something like 11 orders of magnitude. That's a long ways. There's a line, and there's data. And this is how well the data fits this particular model. As you change how hard the collision is, the harder these two particles collide, the more they bounce off each other. And as you change to very high energy, you have a shape. It goes in size 11 orders of magnitude. The line is the theory, and the data is the little marks. And so it agrees more impressively than almost any theory that we're used to in particle physics. That's called quantum chromodynamics, and I'll come back to it as we go. But they recognized that there was a theoretical advance, quantum chromodynamics. We didn't know a lot about it yet. And that there was experimental advance, which I've shown you, the discovery of the top quark, just within the year or two before this study. This is the more complicated picture that I will show you, but not spend a lot of time on, that describes particle physics more generally than just that little short one. So you'll notice in this, I'll just point out a few things, that the structure of particles, of what we're made up of, is on the outside, atoms. Inside is something made of quarks, the neutron and the proton, and then at the very smallest scale, the electron. So that's what we're made of. We have different kinds of constituents that make up the basic ingredients that make up the protons that end up making us up, and those are called different types, which we'll talk about a little bit. Fermions, they're particles that have certain quantum mechanical features, spin a half. Bosons, they're a different family of particles. They have a different spin, 0 or 1. And then there's all the interactions. There's the strong interaction, gravity, the weak interaction, electromagnetic, and strong. We know of 4 interactions in nature, going from the weakest being the one that we in everyday life feel the most, that's gravity, to the strongest, which is what holds us all together, and that's the strong interaction, what holds us together. In between, there's electricity and magnetism, and the weak interaction, which is radioactive decay. Those 4 interactions describe everything that happens on an elementary level. And we're not going to do this. If we did all of elementary particle physics, then I'd fill up my 18 lectures. What I'll do instead is pick some of the areas which are the highlights of where we understand things now and are asking the most important questions as we move forward. So I'll come back to that chart some. This is again 2002. So in 2002, what they did was try to draw a diagram that showed, let's call it the goals of this area of physics, elementary particle physics. And what to take away from this, I'm not forwarding it, this is the picture. So what to take away from it is there's not one goal off in the future, and I wouldn't draw the same chart today quite, but there's several goals that were at that time the biggest, deepest questions that people were asking. They were asking, for example, is there ultimately some unification between these forces? We have reason to believe still that there might be unification between these forces, but we haven't achieved that, either theoretically or experimentally. So that is, if we go to high enough energy, is the electromagnetic force, the weak force, the gravitational force, do they all come together as one force? The second comes out of a set of theories that people have heard about, everybody here, because they're very good at getting in newspapers, called string theory. So string theory has been the biggest hope of the very theoretical physics to develop a real theory of elementary particle physics. It has the problem that it works in dimensions beyond the 4 that we're used to, 3 space-time, 3 space dimensions and 1 time dimension, but rather presently in something like 11 dimensions. And so it's hard for it to predict things in the world we're used to, which is 4 dimensions. It's a very popular subject today and was at that time. And it has the question then of where you go from 4 to 11 dimensions, what we call hidden dimensions. What hides them and how are they? I'll discuss that a little bit. And then what I said at the very beginning, the connections to astrophysics and cosmology, which they saw in this report. So there's a multiplicity of goals. And there's a multiplicity shown down here of different kinds of ways that we have probes to try to understand something, from starting at the left, if you can read it, very rare processes, to a question that's still in the forefront today is, what is the dark matter of the universe? What's the dark energy? And we work in all these different ways to get to some deeper understanding, which is shown in this diagram. We wouldn't draw quite the same diagram today, but the spirit of it, I think, is the same. The spirit of it is interesting because it's different than astronomy. And when I talk about physics, you'll see that we struggle with we struggle with ourselves at all times, much more than an astronomer does. And I'm not saying this negatively about astronomy, but astronomy is basically an observational science. You build an instrument of some type, it may be new and different. You may have some idea why you build it, of course, and then you observe and then try to understand what you observed. In physics, the motivation and the underlying drive is mostly different than that. It's inquiry, what I call inquiry-based. It's based on us asking questions that we think, if we can answer the questions, help us learn more about the physical world, and that's inquiry. And we then do our research, whether it's theoretical or experimental, directed as much as possible at directly answering those questions. So in this report that I'm using as a model for what we'll do as we go to today's questions, is that they formed 11 questions. Again, the spirit of physics, an inquiry-based questions. We'll also be able to look at which ones have been answered in 18 years and which ones haven't been answered in 18 years. So, so there's a set of questions. Let's go on and start to look at those a little bit. So we have an inquiry-based science. First question, one that you read and know and so forth, rather general. How did the universe begin? So how did the universe begin? I got to get to the same place here. Most of physics, as I say, is inquiry-based, and this is an example. One of the biggest questions that we would like to understand is, how did it all begin? We use the word the Big Bang. We've pretty well accepted in the general principle of the Big Bang theory. And we also even are able to measure how long ago the Big Bang happened, 13.7 billion years ago. But we know very little about what happened at the beginning, and there's some big questions. So why do we know so little about what happened at the beginning? Partially, and when I come to it, maybe the answer of eventually getting very close will be gravitational waves. But our main instrument now is through astronomies of some sort, which looks at electromagnetic radiation one way or the other. And at the early times in the universe was so dense that electromagnetic radiation couldn't get out. So we can only go back with whatever is measured to 400,000 years after the Big Bang. So everything you know about what happened in the Big Bang, the stories that are told, or the story that I'll tell, you have to realize it's got a certain amount of inference and imagination in describing what happens at the very early times. Why do we care? Well, I'll give you one reason. There's many reasons. We want to know why it started and so forth, but there's one very obvious one, and that is we live in what, as physicists, we call a matter-dominated universe. So what does that mean? That means that we are all made out of protons and neutrons, not out of antiprotons or antineutrons. Well, if we go in the lab, we go into CERN laboratory or something, and we all know from Einstein's equations, you can change energy into matter. it's democratic. It'll make as much antimatter as matter. So in the early universe, we presumably had a very hot so-called Big Bang. We had a lot of energy. The energy turned into matter. Why didn't it make an exact equal number of matter and antimatter? In which case, they would have annihilated each other, and we wouldn't be here. So there was something in the early universe that was different enough to make, in the end, now, 13.7 billion years later, a matter-dominated universe. And there are different ideas. We don't have and won't have on our list of questions that we make now a way to answer that quickly. We have some ideas, theoretically, of what might be necessary to make a small, very tiny asymmetry in how much matter and antimatter you create from Einstein's E equals mc squared. Two facts that people are trying to see experimentally that might be part of the answer, we don't really have a theory, is whether protons that we're all made of have a finite life. That is, they somehow decay eventually. If that's true, that helps you develop a theory that is not symmetrical. But we already know from tests, experiments, mostly one done in Japan, that the lifetime of a single proton is a lot longer than your lifetime. It's 10 to the 35 years. Nevertheless, it could be that it only lives 10 to the 36 years, in which case it could help this problem. So there's new experiments being developed now, mostly in Japan, to see the next 10 factor of 10, whether the proton has a finite lifetime. The second one, which is what we're actively looking at, and I don't know if we're on the right track at all, but motivated by the same long-term goal of trying to explain why we have a matter-dominated universe, is whether there's some sort of asymmetry in particles that we call neutrinos. I'll talk about neutrinos. I said I was really going to emphasize neutrinos just before Christmas, between early December, those lectures, because it has so many interesting aspects. And if neutrinos themselves have some sort of asymmetry, the asymmetry that we talk about is when you look in a mirror, do you see exactly yourself in the reflection or something slightly different than yourself in a reflection? And that question for neutrinos is one that's actively being probed. So it may be that the direction we're going is completely wrong in terms of explaining a matter-dominated universe, or maybe some of the experiments that I'll describe as the course goes on, the neutrino experiment and the experiment to look at the proton lifetime, both are actually done in the same apparatus, can give us clues, will give us clues. So at some stage, we'll come back to this question without really knowing whether we're going to quickly know the answer to it, but clearly it matters to all of us because we are here. So next, all right, I want to emphasize that since 2000, we've answered some of the questions that are posed in this 2002 question. And I show some of that here. And I show it here to emphasize that it's not the same as this study. We've moved on, answered some of the questions. There are some new questions, and some of them still remain, like the ones about the early universe. So there's three big discoveries that have something in common, which I'll mention now. First one is the discovery of what's called the Higgs boson. That was an important discovery. It came 60 years after the idea that there should be such a particle existed was made by Mr. Higgs and two other theoretical physicists. It was discovered at the CERN laboratory in 2011 and resulted in a Nobel Prize for the theorists who proposed the theory. But what to notice here, in addition to anything else, if any of you have ever been at CERN, and I'll show this later, is that it is a monument almost to modern technology to build the experiment that was required to actually see this particle. It didn't take 60 years because we're dumb. It took 60 years because you had to develop the right technologies, including the accelerator and the detectors that were used to detect that. The second that I show is the detector that has been used so far to study the proton decay that I told you has a lifetime of 10 to the 35 years or greater, and to study the properties of neutrinos, some of them that I'll talk about in December. And that is that the neutrinos have this ability to change their identity from one to another kind of neutrino, which is a strange phenomenon, and I'll show you that in December. That experiment was also extremely high tech. It involves many thousands of the most sensitive and largest photomultiplier to see flashes of light, surrounding the clearest water in the world in a huge, huge tank of water deep underground. This was a monumental effort to build this detector, which is called Kamioka, or Kamiokande, which is the Japanese name of the mountain that it's under. And it's extremely high tech again. And the third one is my field, and also being done here by my colleagues at University of Rome, and that is gravitational waves. It took us 100 years to develop the technology to actually detect gravitational waves, as you'll find out, because they require the most accurate measurements, to a measurement of 1 part in 10 to the 21 in order to measure gravitational waves. I'm not going to show you those details today, but rather I'm emphasizing that we've moved into a world where asking and answering the most difficult physics and most basic and important physics questions require what I call large-scale experiments. So these large-scale experiments have a huge amount of technology in them, and it's essentially a major way that physics is going forward now and will in the future. That doesn't mean there isn't somebody who will invent something in their lab. That will happen, but more and more the advances in physics are happening because of very large-scale collaborations using the most high technology techniques in very large detectors. This is just to show you beyond those three that actually discovered something. There's a very large neutrino experiment. I said I'll talk about neutrinos. Fantastic device put by drilling with hot water deep under the ice cap in Antarctica at the South Pole itself, using a hot water drill and then putting photomultipliers deep under the surface of the ice, where the ice is very clear, and you can actually see the deposition of the interaction of neutrinos deep under the ground that came from distant sources, not from an accelerator like we looked at before, but from somewhere in the cosmos. And they've identified at least one source that basically gives these neutrinos. Why is that interesting? We don't know yet where cosmic rays come from, how they originated. We have cosmic rays that go to energies far beyond we can make on any particle accelerator, but we don't, and they come through you and me and everything every day, but we don't really understand the physics of how they were produced. We have some ideas, and I'll show you that, but we don't really understand the physics of how they were produced. So that's the one on the left. The one on the right is our best knowledge of what happened in this early universe that I talked about. That's a picture of the universe at 400,000 years after the Big Bang, looking at what's called the cosmic microwave background. We'll talk about that later, where at first it was good to see that the universe is expanding as expected in some uniform way, but the asymmetries in it give us information that goes well beyond that. And so these are all what I call forefront large-scale experiments. Okay, the second question, and again, one that we haven't answered yet, but was on the table as one of the 11 questions in 2002, was what is the dark matter? So what are we talking about in dark matter? Interestingly, the universe that we know about now, we know enough to know that only 4% of what's in the universe is normal matter that we all know, whether matter like ourselves or stars or whatever it's made of. If you add it all up, it only adds up to 4% of what's there. Something like 21% is a form of matter, but somehow doesn't give any detection that we can see, so we call it, which is mostly electromagnetic detection, which we call dark. So that's called dark matter. A third is that there's more energy that we can't explain, and this manifests itself in the universe expanding at an increasing rate from everything we measure. And so most of what's in the universe we can't describe yet. Dark energy is the second question. It'll be on here, I think. But dark matter is a very, we think, should be an accessible topic. So it's on their list in 2002. It's even more on the list that we'll make here for 2019 for what the future is. And the reason is that we know enough to know that it has to be either something's wrong with the theory, which would be interesting, or there's some features that it has that should make it accessible. That it's a kind of particle, we think, not some big masses. And those particles, there's different explanations for what those particles might be, but there's different particles, and they basically have characteristics that we could detect, and there's a variety of experiments all over the world, including very ambitious ones here in Italy, in the Gran Sasso mountain, to look for the dark matter. We'll look at all that as I go on, but it's again one of the puzzles. I think we should take a break, and then I'll keep going. So we'll take a 15-minute break.
Seduti per favore.
Okay, welcome back. So I'm going to continue with this report, and then we'll go on. So when I ended, I talked about dark matter, which makes up a big piece of the universe, what's in the universe. And we also have what's called dark energy. This is interesting in the spirit of what I'm talking about here, because it's a newer problem. And one that we really don't understand very well. The universe is not only expanding, something we learned not so long ago, but it is expanding faster and faster. And that's a very difficult concept to reconcile with how we understand nature. So we basically now have to understand dark energy. Mostly, at this stage, we don't have a good key to what to go measure, to really understand dark energy. So instead, and I'll talk about it some next spring when I talk about this kind of subject, next March or something, it's mostly now experiments that can characterize it so we can understand it. What are the features of dark energy? And I'll show you an experiment that's being built as we're meeting here called LSST, which has a big goal to understand what we call the equation of state, or the characterization of what's called dark energy. So even though this was posed in 2002, this is one we haven't made a lot of progress on. I'm optimistic that we will, but it'll take time. Okay. The next question posed in 2002 was interesting. And that is, did Einstein have the last word on gravity? So clearly I'm going to talk about gravitational waves in January. I'll just say a few words right now about gravitational waves, but this question is broader than just gravitational waves. Why did we end up with a theory of gravity that came from Einstein anyway? Let me remind you. So when I was a child, when all of you were children, you went to school, and your teacher told you about the apple falling out of the tree, and when you jumped up, the earth pulled you down. And that idea came about, what was happening came about from a theory, probably, arguably, the most successful physics theory of all time, by Sir Isaac Newton in 1687. So in 1687, Isaac Newton wrote a book called the Principia. And in that book, he described his theory of gravity. His theory of gravity was here. His theory of gravity, he called universal gravity. This was a huge thing because he managed to write down one equation, the equation here, that described gravity everywhere. So it was not apparent that why the moon goes around the earth has the same explanation of why the apple falls to the ground. But in Newton's theory of gravity, he explained that and many phenomena that were only looked at later. For example, why there are tides in the water, the description of all the planets. And so Newton wrote down an equation, which we all learned at some point. And that is, the force of gravity between two objects is inversely proportional to how far they're apart squared, and proportional to the product of how heavy each is, what the masses are of the two. And even in that book, and the strength of it was some unknown constant. It's called G in the formula up here. It took another 100 years to figure out what G was, by the way. But that was the formula. And in the book, he did all the calculus to show that you can take the center, what we call the center of gravity of each of the objects, and so you can measure the R in between. This was a fantastically successful theory. It basically described everything about gravity for more than 200 years, with the exception of only one observational phenomenon. And that observational phenomena was the orbit of Mercury around the sun. And basically, he described that all the planets and their orbits and so forth around the sun, but there was one exception. And that was the orbit of Mercury around the sun. Mercury is our planet, to remind you, that's closest to the sun. And when it goes around the sun, it has a very, what we call elliptical orbit. It goes way out and then it comes back. And because of the positions of all the planets and moons, it doesn't go back to quite the same place. And you can calculate where it should go back when it goes back from Newton's formula. and the positions of all the planets and so forth. And you get an answer that's close, but it's the wrong answer. It's about 10% wrong. So this was the only puzzle that existed at the time Einstein came along. I'll tell you more when I talk about gravitational waves, what happened in those years in between. But for today, there was no other discrepancy when Einstein came along. So Einstein gave us a new theory of gravity. Even though there was only one puzzle, that puzzle was not taken that seriously because we were not that capable experimentally to tell that there wasn't some other object between Mercury and the Sun that would explain this small discrepancy. So Einstein's theory of gravity, basically, why do we need it if Newton's theory worked for everything? And we needed it for a couple reasons which Einstein recognized. Two reasons. One is when the apple falls from the tree, in Newton's theory, you see it and know about it immediately. But in Einstein's case, he's worried about what happens in the universe. And if the sun were to burn out or leave or disappear right now, it would take 8 minutes for us to know, because that's the time it takes for light to come from the sun to us. So it takes 8 minutes. It wouldn't take gravity 0 time to tell us. So in Einstein's theory, it also takes 8 minutes for anything that happens to get to us, the same speed as what we call the speed of light. And this is needed to do anything in astronomy, distant objects, how far apart away they are, how long it takes the signal to get to us, and it's used all the time in astronomy. So that was the first reason that we needed a new theory of gravity. The second is that when you were a kid and your teacher told you that when you jump up, the Earth pulls you down, did you ever ask why? Because Newton's theory never explained why the apple is attracted to the Earth. Einstein's theory, which we'll talk about later, explains it in a way that's a little abstract. It combines space and time together, which we'll talk about later. But the words you know, there's a warpage of space-time. It's this distortion of space that makes a path by which the apple falls to the Earth, or by which the Earth goes around the sun. So you can explain why it happens with Einstein's theory. So this is a illustration of how science moves forward. Newton wasn't wrong, but we had a wonderful theory of gravity from Newton. But eventually, we find that we need a more sophisticated theory of gravity to explain some phenomenon that Newton's theory doesn't. So Newton's theory doesn't do anything wrong. It just doesn't include what we need to have finite speed of information to get from wherever something happens to us, and to explain why, which he didn't explain. And that Einstein did in his theory. That theory then basically is used a lot. It's used in astronomy to It's used in astronomy now to see the big experiment that was done that proved Einstein's theory was to see that light bent. This is because of a warpage of space and time, and I'll describe that experiment in January. But what that has done is mean because light bends, you're able to do something that's done all the time in astronomy, which is to look at something called gravitational lensing. So it's an illustration, which I'll describe later, that making a new discovery often gives you new power. In this case, power to study objects through what we call gravitational lensing. And there's a picture of gravitational lensing. The first one is light coming around a dark object. And the second one is the most famous one that you can see if you're really lucky, even with the naked eye. So it's called the Einstein cross. Those four dots around are from an object behind making the light. And that is, again, an illustration of a phenomenon that couldn't have been predicted by Newton, but came from Einstein's theory. A year later, after Einstein introduced the theory, he introduced something else. But first, let me just show this. One of the big things that we do as physicists is try to test, and that was the spirit of this question, whether Einstein's theory is right. And it makes a lot of detailed predictions that you can test. Those predictions have subtleties in them, but there are some very special experiments that have been done to test those. The one that I show here is an experiment that was done to look at what you call the precessions that happen when objects go around each other, and what we call frame dragging. I don't have time today to go through those, but there's a very sophisticated satellite experiment that so far has given a result that's consistent with Einstein's theory. And this is the fact that the Earth is spinning, how it affects the object that's up in the satellite, and so forth. And so we're testing Einstein's theory in various ways. He also, which is usually important if you have a new theory, isn't just to explain things that you couldn't quite explain before, but to predict something new. He predicted the bending of light, but he also predicted gravitational waves. And gravitational waves are what we'll talk about in January, and they came about in his original paper, which is shown here. I'm going to skip that. In his original paper, he wrote in 1916, he basically noticed that if he set up general relativity in a particular way, the equations looked like the equations of electricity and magnetism. And we know for electricity and magnetism that there is not just electricity and magnetism, but electromagnetic waves. And so electromagnetic waves come out of the equations, the so-called wave equation that we get. And so since he saw the same form of an equation, he didn't derive from first principles that there were gravitational waves. But being Einstein, he made the leap that if the equations had this indication, there must be gravitational waves. So he wrote a little paper in 1916 where he predicted that there would be gravitational waves. He also suggested that the effect of gravitational waves were so small that they probably couldn't be tested. And that was wrong because we managed to test it, but he couldn't envision modern lasers and optics and things that we can do 100 years later that couldn't have been done in Einstein's time. So he predicted gravitational waves, and of course we've managed to see them in the last year or so, and the last couple of years, both in the US and here in Italy. And the technique and so forth I'll come back and describe, only that it so far now is a testing ground that first there's something Einstein predicted, and now we can use this as a very rigorous way to test whether Einstein's theory in detail is right, or maybe alternate theories that have some deviations are better theories. And it's again the way science moves forward. So far, Einstein's theory is right. This is just to show you once the picture of the discovery of gravitational waves. Those are waves, as you can see. The waves get bigger as they go along. The scale is 0.2 of 1 second. The vertical scale is this 10 to the minus 21, the size of the effect that we measure. You can see they get a little taller at each one and narrower. That's the characteristic shape that you expect from Einstein. Without going through it today, look at the picture on the right, if I can make it. And you'll notice the top two traces are the same pictures I just showed. So those are the data. The second line, which is here, is the calculations using Einstein's equations. And you can see that it looks essentially, except for ours being jagged because they're experimental, they look the same. And if you subtract one from the other, you get this picture here. And you see there's no indication of anything but just the inaccuracy of our instruments, or what we call noise. So this was a validation of that aspect of Einstein's theory. And we'll talk much more about that in January. Now I want to go on to the next question that they have. And the next question in 2002 is, what are the masses of the neutrinos, and how have they shaped the evolution of the universe? This is an interesting question because I told you that we now explain masses which they couldn't then as the Higgs particle. So we have a mechanism, which I'll talk about a little later, to explain masses, and a discovery that was made since this report, but in 2011. And it describes for us the masses of the quarks and particles. But there's still a puzzle. It does not describe the masses of the neutrinos. The masses of the neutrinos don't come from this mechanism. So we still don't understand something about mass, even with this new mechanism. So neutrinos are really puzzling, and we'll be studying those in the lectures in December. In terms of progress since the 2002 report on neutrinos, what we've understood much, much better is how they transform one to another. And I'll talk about that all in December. But the fundamental question of where the neutrino masses come from, which one is heavier than the other ones, and so forth, remain to be seen. And I'll show you why that's important and what we're doing experimentally to try to attack the question. So in nature, and on the picture that I drew, there are three neutrinos. We label them neutrino with a subscript E, neutrino with a subscript mu, and a neutrino with a subscript tau in the upper left-hand corner. Those are the three neutrinos. They go along with these three families of quarks that we have, that I showed on that one picture. What wasn't known until shortly before this report that we're talking about today is that these neutrinos have mass and transform one to the other. Like often happens in science, then there's the next question. We now know that they have mass, but if you look at the picture on the right-hand side on the top, you see three lines of different spacing. And what that's telling us is we know that they have mass, but we don't know which one is heavier than which. Why does it matter? Maybe they have the same order as the other particles that are charged, or maybe they don't. If they do have the same order, it sends us theoretically in our explanation of the particles in a different direction than if they're opposite. So there's kind of two classes of theories that people use that depend on the two. Another thing that we don't know, we know something about, I keep saying neutrinos have mass. It's not quite what we know. What we know is that the neutrinos, if you give them time and space, like coming from the sun to us, transform their identity one to another. We call that neutrino oscillations, and I'll spend some time on that in December. That tells us that one neutrino is heavier than the other and it transforms. I'll explain that. But we don't know the scale at all. We don't know how massive these neutrinos are. We just know something about the difference in mass between them. And so there are a special set of experiments that are trying to measure this finite mass itself. It hasn't been done yet. And what I'm showing in the bottom slide here, and I'll show you the experiments later, it's one of the modern hardest experiments being done, is to measure something which I call a Curie plot here, near the endpoint. So what is a Curie plot and what's the endpoint? If I have some unstable particle, even a neutron, and it decays, or a pi meson, and it decays, and it gives neutrinos in its final state. The neutrino can only go up to some energy depending on what its mass is. So if I measure the very final state at the very end and see where it cuts off, it would cut off here if it had 0 mass, but if it weighs a little bit, it cuts off earlier. So I have to measure this little difference at the end, which turns out to be a very, very difficult job, but a very important problem in physics. So there's a very ambitious experiment being done in Germany to try to measure this little difference. Experiments that have tried so far have failed. So we know a limit, it can't be bigger than something, but we don't yet have a measurement. And so it is one of the questions that I would put on our new list of one that we're going to measure. And I'll show you in December, I'll show you what the experiment looks like to try to measure that. Next. Okay, I mentioned this a little bit, but we don't understand it. And that is, they bring the question here because this report is trying to bring physics closer to astronomy. That was the purpose of the report. One of the questions that was addressed or noticed is that we have all the cosmic rays that come to the Earth, but we don't really have a good explanation for how they originated, what the physics is. We have different model pictures, and I'll show here the picture that we have, which is that there's various mechanisms around stars, for example, and galaxies that accelerate particles just because of they have charges, and charges attract each other, and heavier particles annihilate and make lighter ones. And those, without going through any details, those pictures are shown here, but they're only pictures. So we don't really understand them. When we talk about the very highest energy ones, way, 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 way beyond anything we can make at CERN or on a particle accelerator, what is it in nature that enabled nature to make particles that are so much more energetic than we can make on the most powerful particle accelerators in the world? And that's not understood. And the characteristic of the high energy, say neutrinos or particles, are just being studied for that reason, to try to understand what their nature looks like so we can get some clue to how they were made. And so that's another question which is being posed. I mentioned this one already, and that is the proton stable? And that matters, we think, if we want an explanation for why we're in this matter-dominated universe that goes along the lines of our present thinking. Maybe it is stable and we're thinking the wrong way. We don't know why we have a matter-dominated universe. All I was telling you is that whatever ideas we have focus on two physical phenomena. One is the proton having finite lifetime, and the other is the neutrinos looking a little different in a mirror than they look themselves, what we call CP violation. So anyway, this is the next question asked in 2002. We still ask it today. This is a picture of the beginning of the universe and how we see it now, which I'll go through in much more detail later. But at the beginning, we had some Big Bang, we call it. Then, at the very early instance of time, different things happened, but one that we don't explain at all, but we infer from the measurements we've made, is that there was a period which we call inflation. What that means is that the universe started with a lot of energy, started making, when it cooled enough particles, and they somehow accelerated faster than you'd expect just in expansion from the energy. So it's like, money gets worth less faster, so we call it inflation. And it's something that we infer from today's data. It's something that there's different models and pictures of it, and it's something we need to understand. So understanding the early universe is crucial to addressing questions like that. And we have a variety of probes that aren't going to definitively answer it. I mentioned earlier, in my view, the way to get to the very early universe best is either isn't with electromagnetic probes, which is what we use now because of this absorption at 400,000 years. So if we want to go earlier physically and see something, there's two possibilities. One is you use neutrinos. They don't get absorbed. But neutrinos are very elusive particles and very difficult to do. And so it's probably not practical, even though it's okay. And it could come within, I think it's 3 seconds of the Big Bang. So you could get back, instead of to 400,000 years after the Big Bang, to 3 seconds after the Big Bang. But we don't know how to do that. The other is with gravitational waves. And they would get back to the very first instance. We also don't know how to do that yet, but we're in the very beginning of a field that we're learning how to do things. So my guess is that eventually the way we'll get back to the early universe is with gravitational waves, but not in the next couple of years, I don't think. This is the search for proton decay, which I told you is crucial to this. And this is the picture of the big detector in Japan, made out of pure water. And you can see the dimensions, which I didn't say before. It's as big, it's a circle as big as a football field, 74 meters almost. But it's also 78 meters high. So imagine something about the size of a football field, also as high, that high, all full of the purest water in the world, being viewed all the way around it with photosensitive devices that are used then to recreate anything that happens due to particles coming in and interacting in the volume itself. So that's called Kamioka. And within the last 10 days, I don't remember exactly, the Japanese government has given the indication that they're going to support the next version of this, which is roughly 10 times bigger. So in terms of future experiments, there's going to be something they called this, the first one Kamioka, which was smaller than what I'm showing you. This one they called Super Kamiokanda. And the next one will be called Hyper Kamiokanda. So it'll be built over the next decade, I suppose. Okay, this is a different kind of interesting question, and that is, in the universe, at the very earliest times, matter was being made. Things were really incredibly dense because it was close together. So do we understand the physics when we have these very, very high densities of particles and very high temperatures? And that is, again, needed if we want to understand what happened at the time of the very early universe. When we look at the so-called evolution of the universe, what happened at the very earliest times. We have an experimental way to get at that, and it's being done. And that is to take not protons and electrons and neutrinos that I've been talking about so far, which are elementary particles, but instead take heavy particles, heavy ion particles, and smash them together. And in that way, they can create some of the conditions of the early universe. And that's being done in what the words that are used, a quark-gluon plasma. They're able to create a gas, basically, of high density that is made out of quarks and gluons that hold everything together. And the graph on the left, which I'm not going to explain today, tells you the region that they're able to cover that covers the same science that happened in the early universe itself. So these are experiments that are being done using colliding particles, like on particle accelerators, but heavy ions, for example, at the Brookhaven lab in Long Island, New York, and to some extent at CERN. Okay. So in the questions, this is another interesting one. I mentioned sometime in the last 2 hours string theory. String theory has the interesting feature that not only has a bad feature that all the calculations are in multiple dimensions, like 11 dimensions. So it's hard to predict, make it a theory that's predictive, as beautiful as it is theoretically, predictive in the world we live in. We live in a 4-dimensional world, 3 space, 1 time. I do experiments in this world, so what is it, something that predicts in 11 dimensions to? In the theory, they take the 11 dimensions and they, because we live in a 4-dimensional world, 3 space and 1 time, they say those dimensions just are invisible to us. They curl up on the scales that we look at. And you can imagine that doing that is not unique. I can curl it up one way and you can curl it up a different way. So it isn't really a predictive theory. And that's the reason people criticize string theory, even though it's such a wonderful theoretical theory, it's not testable because it works in 11 dimensions. So that's the criticism of it. And it's not unique how you get from 11 to 4 dimensions. You have to curl it up, but I might curl it one way, you might curl it another way. But another feature of it is that it might imply that some of the dimensions are just hidden. We're not able to see them in the world we usually work in. And in most of those ideas, the hidden dimensions are in gravity. And so there's basically ideas that you could see dimensions, I kind of show it here, that are only seeable in gravity. That our world is the left one on the top, but there's a world next to it that in gravitational effects is there, but not in the world that we see every day, and that those are something we can see. So there's an attempt to see how we might see these hidden worlds experimentally. And there's various ideas. They're not very mature, but they may get there. There's nothing fundamental. Problem is kind of newish ideas, and it depends on the theory, which has many forms, what these hidden dimensions might look like and how you might look for them. But it's a place where theory's not very definite, where experiments maybe can start to address the question, and hidden dimensions is a very interesting topic for the future. And I'd say it's more interesting now than it was in 2002, even though it's really a long-range thing. Although it could be the kind of phenomenon where somebody just makes a big discovery. But in terms of kind of systematically addressing it, it's not very addressable right now. Okay. This is an interesting question, and one that my colleagues and I answered. Maybe, with a great big maybe. So an interesting question is, where did your favorite heavy elements, maybe that some of you have in your finger, like gold and platinum, come from? How did they get in the earth? Physicists have, of course, noticed that we have heavy elements in the earth. And it's our job to try to explain everything. So we try to explain it. So why is there a puzzle? There's a puzzle because most of the universe is made out of what? It's made out of hydrogen and helium. That's basically what the universe is. Then there's stars. Stars start by being made of whatever elements are there, and they burn by the nuclear fusion process. The same process that's in a hydrogen bomb and the same process that's being developed in places like the ITER facility in France that's trying to make an energy source out of fusion. So the fusion process is used to make stars burn. That's well accepted. So the sun keeps us warm by burning. and all the stars burn. First they burn hydrogen and helium. When they burn up the light elements, they go on to lithium, oxygen, and the fusion process works and keeps burning until it gets to about iron. And at that level, the fusion process doesn't work anymore. So stars eventually burn up their fuel, and when they burn up the fuel, before they burn up the fuel, there's an outward pressure from the fusion process, and it emits light and heat to keep us warm and so forth. And gravity's trying to pull it in. And when it finally burns up its fuel, a star, gravity wins, and it collapses. And when it collapses, that collapse basically is the end of a star. But it didn't go beyond iron. We'll talk about the collapse of stars later. But it didn't go beyond iron. We only burned up to iron. And so where did platinum, gold, uranium, whatever come from? And that's been a puzzle. The explanation that physicists have had for years is there must be a process that's rare, that's usually rare, that gets stimulated or increased in the sun. And we have it a name. It's called the R process. It's the name just given to the process. Only because we observe heavy elements have people tried to make it enhance the production of heavy elements, even though it doesn't usually happen in fusion, from this nuclear process, and use that to explain how heavy elements came. How do we even know there are heavy elements in our periodic table? I don't know if I have a picture of the periodic table here. No. But if you look at the periodic table, it goes way beyond iron and gold. So how do we know that there are the heavy elements? We make them in the lab, and we know how to make them in the lab. You take a heavy element, and you bombard it with a lot of neutrons, and you make a heavier one. And if no one's seen it before, you name it, and you have your name in the periodic table. And that's how the heavy elements are made. So it turns out that and again, I'll show you when we come to gravitational waves, that in addition to the first observation of the gravitational waves, we've seen one example so far that we've reported of the collision of not black holes, which is the original observation, but what are called neutron stars. Notice the name neutron. And remember what I said you do to make heavy elements. You bombard a heavy element with lots of neutrons. A neutron star is the product of one of these stars that has burned its fuel, collapsed, makes a very dense nuclear object with lots and lots of neutrons. We observed two neutron stars hitting each other. That sounds a lot like what happens in the lab. And at least by a calculation, since we've only observed one, it's consistent. You can make a consistent story, not a proof, but a consistent story that that's the predominant way that many of the heavy elements were made, by neutron stars colliding in the past sometime. So this one is partially answered, maybe answered. That's just our artist. So what I was saying is, for example, platinum and gold, that's maybe came from something we observed in gravitational waves. That calculation, by the way, which I show here, said that in our observation, the amount of gold that was emitted was about 100 Earth masses in the one collision that we saw. So these can be very, very strong sources of gold. And maybe that's where they came from in the Earth. It's right now, I think, a better story than the old one. So we have a good story. And again, is an illustration of the stepwise progress of science. Okay. So the next question is really got to do with what I was saying, string theory, or something like string theory. A theory like that solves a lot of, in addition to the experimental problems, which I'm the one concentrating on in this talk. If I was a theorist standing here giving this series of talks, I'd concentrate on a whole bunch of theoretical problems we have in the present theories. And we know that string theory might be one of the answers or something else, but as I said, the fact that presently we don't have a good way to test it, we're not able to grab on and use theories that solve theoretical problems. So string theory is an example of a theory that is a lot of fun for theorists because there's a lot of very interesting mathematics, and they've developed some new mathematics just to do the theory. But it also has the feature that it solves a whole bunch of theoretical difficulties we have in the present theories. And I mentioned the present theory is a model, not a theory. So it sounds very good, but we have this problem that the closest we can come right now to a place to test it is to look for extra dimensions. Second possibilities might be some physics that would be in black holes, but that also isn't very definitive. Okay. So I guess that's telling me we're done for today. And thanks for coming. And those of you that come back, I'll see you next week.